Our final unit in Calc 2 is polar graphing and polar coordinates, which to me is some of the prettiest graphing you can do. And it gives us just kind of an interesting way to end the year. So our polar coordinate system, we're going to kind of not do calculus right away and get to some of the background information first. Polar coordinate system is graphed very differently. We don't graph things with x's and y. We don't have points that are written as an x and a y. Instead, we have what's called a polar system, which is going to be given by a point that is r theta. R is going to be a length. It's going to be a radius. Theta is going to be the angle that is made between the polar axis and the directed distance. So I have a picture here to kind of help you. So your polar axis is the one that's going to run this way. It's just going to point to the right like this. My angle is going to open in a counterclockwise direction, kind of thinking the way it goes around like the quadrants. And my angle is going to be the theta value, how far out that kind of extends. My directed distance is where the point is going. So this is your length r from the middle. This is called the pole out. So your point is actually going to be written kind of like as a dot here that you're going to plot that is r distance away from the pole and at an angle of theta. So the best way to explain it is just to do it. Now, when you graph these, you don't graph it on a traditional XY coordinate plane. Instead, you graph it on more of a unit circle plotting. So I have two blank plots just so you get a chance to kind of get them marked up. And I have 5 points that I'm going to graph. So I'm going to start with the very first point, A, 2 pi over 3. So what you do, you actually graph the angle first. So you're going to start at 0 on your polar axis, and you're going to go until we get to pi over 3. How many rings you go out is going to be your radius. So the very center, that really, really dark black in the middle, that's your pole. So from that pole position, you're going to go out 2 rings, and you're going to plot a point right here. That is going to be point A. So it goes an angle of pi over 3 and then out 2 rings or 2 units on its radius to get that point. For B, now if it has a negative angle, you're going to head in the opposite direction. So a negative angle is you're going to go this way. Negative pi over 6 is actually going to end up at 11 pi over 6. And then you're going to go out 3 rings or 3 radial lengths. So we're going to go from the pole towards 11 pi over 6. 1, 2, 3. Put a point there. And we're going to call that B. C is going pi over 4, so it's positive, so we're going back to the normal kind of counterclockwise direction. But once we get to pi over 4, which is right here, instead of moving in the positive direction, which would be heading towards pi over 4, we're actually going to backtrack from the pole. So we're going to go in reverse. So instead of going this way, we're going to go this way. So point C is going to end up, I'm going to go across from pi over 4. It's going to end up right here. Kind of hard to see. So that's point C, not A. Sorry about that. So you're going to get rid of that. You're going to end up right here. And we're going to call that point C. So we go the direction of pi over 4, but then we go backwards 1. D, I'm going to put this on the second one just because I feel like the first graph's getting kind of messy. You have a negative angle, so we're going to go this way, negative pi over 3, which is actually going to take us to 5 pi over 3. But then instead of going towards 5 pi over 3, we have a negative radial value, a negative radius, so we're going to back step 2 units. So pi over 3, we're going to go backwards 1, 2. That's going to be point D. And then finally, E is 0 pi. So your pi is going to go all the way out, all the way around here. However, since your radius is 0, you're not going anywhere. This is just going to be at the pole. Anytime you have a 0 as your radius, no matter what your angle is, you're always going to be graphing at the very center or at the pole. So that's how you do some basic graphing. Now, what you might notice is, unlike rectangular coordinates where each point is very unique, if I ask you to graph the point 2, 5, then the only way to write it is 2, 5, and there's only one place to graph it. Polar isn't like that. I actually have many different ways to plot the exact same point. For example, I'm going to use A as the easiest example because A has a very basic graphing, but a lot of ways we can write it. Another way to write a point is to do an extra revolution. What I mean by that is if you add 2 pi to the pi over 3, you're going to basically go all the way around the circle and then to pi over 3. So if we take 2 pi plus pi over 3, we would get 8 pi over 3. So another way to write point A would be 8 pi over 3. Again, all we're doing is keeping the radius the same and then adding 2 pi to the angle. Another option is you could use negative values. So if I want to get to 2 comma pi over 3, I could go in this direction to negative 4 pi over 3 and then go in the negative direction in order to get to the same point. So for example, negative 2, negative 2 pi over 3 would give me at the exact same point. So I'm going negative 2 pi over 3. That takes me over here. But then I'm backstepping too. Another option is to go all the way around in the negative direction until we get to pi over 3. So that would be negative 5 pi over 3, but then going out 2 units. And again, there's a limitless number of points that I could write that still would get to me to the same spot because I could just keep going around an extra rotation over and over and over again and just keep getting the same point over and over and over again. So it is not unique for polar like it is for rectangular, which is the point I'm trying to get across. Part of what we're going to do kind of together is to practice graphing and to be able to represent points in different forms. Coordinate conversion means going back and forth, kind of like what we did with parametric, between rectangular and polar. So if I give you something that is in polar, you should be able to tell me the equivalent rectangular and vice versa. Now we have a couple formulas that help us do that, so you might want to jot this down somewhere. If we're given polar and we have to go to rectangular, which is the easier of the two, you're going to use these two forms, x equals r cosine and y equals r sine. We're actually going to use these two formulas a lot in this entire unit, so it's definitely something you want to kind of write down. All of these values come from using basic trig and basic ideas from the unit circle. That's where these formulas come from. A lot of unit circle knowledge going on here. If I want to go in reverse, if I want to have rectangular and switch to polar, I use these two formulas. Again, a lot of things that are very trig-based, very Pythagorean-based, very unit circle-based. So for example, let's say I have the polar point 2 pi. So that is your r and that is your theta. If I want to figure out the xy coordinate that corresponds to that, to find x, I'm going to do r, which is 2, cosine theta, which is pi. Cosine of pi is negative 1, so I get negative 2. And then for y, I would do r times the sine of theta, which is pi. Sine of pi is 0. So what that means is if I were to graph 2 comma pi on the polar graphing system, it would equate to negative 2, 0 on the Cartesian plane. Not too bad to work with. Obviously, there's some unit circle knowledge that comes into play that helps you. Going in reverse is a little more work. So to kind of show you going in reverse, let's say we have an xy that is the point, we're going to do something real simple. We're going to do negative 1, 1. So that is your x and that is your y. And the goal is to write the polar coordinate that corresponds to the Cartesian negative 1, 1. So first we're going to get our angle. So we're going to say that the tangent of theta is equal to y over x. This again comes from basic like SOHCAHTOA. So y is 1 over negative 1. So we have the tangent of theta equals negative 1. So we need to know what angle, when I take the tangent of it, do I get negative 1? That is 3 pi over 4. Again, a lot of unit circle knowledge going on here. That's our angle. And then to find my r value is going to be r squared equals x squared plus y squared. So we get r squared equals 2 take the square root of both sides. You get r equals the square root of 2. So my polar coordinate, and this would not be the only answer, there are more angles than that, as we talked about, this is not unique, is the square root of 2, 3 pi over 4. So we can take polar coordinates and make them rectangular. We can take rectangular and make them polar, and we should be able to plot polar using a polar grid.